Okay, so hello everybody, and thank you for joining and welcome to our webinar entitled Conquering Complexity, Refactoring JavaScript Projects, where we invite you to learn how to identify unnecessary complexity in your codebase using cognitive complexity as a measure, and what tools are available to help you refactor. As a bonus, I believe we will be treated to a live example. I'm Andrew, your moderator for this webinar, which will be presented by Phil Nash, our developer advocate for JavaScript at Sonar. Before I introduce Phil, please allow me to quickly go over the essential housekeeping points. The session will last around 30 minutes, and we will include a time for questions and answers at the end. You are invited to submit your questions at any time during the webinar via the Q&A box in Zoom. So that's the little icon in the middle of your bottom toolbar in Zoom. So please do submit your questions at any time using that Q&A box. And we have two panelists joining us, Victor and Tibor from our JavaScript squad, plus Kenny from our APJ office. So they are tasked with answering as many of your questions live during the webinar. So do feel free to submit your questions at any time. Don't wait till the end. The session will be recorded and we'll send out a link via email in the coming days. So you will get a link to the recording. Finally, at the end of the webinar, a short survey will pop up on your screen. So we consider your feedback as a gift. Thank you in advance for your participation. Without further ado, I'd like to introduce you to today's presenter. Phil, over to you.
Thanks very much, Andrew. And hello and good afternoon, good evening, good morning to wherever you are. My name is Phil Nash. I am a developer advocate here at Sonar for JavaScript and TypeScript. And I'm very excited to talk to you about refactoring that JavaScript today. If you are ever got questions, like if you have questions today, get them into the Q&A box. But if you think of other questions or you want to get in touch with me any other way, you can find me all over the internet as Phil Nash on Twitter, on LinkedIn, or just hit my website, which is my favorite URL in the world because it is just Phil Nash. I'm just delighted by that. I'm also into interactivity in these talks. So if you do have kind of comments or things you want to say as part of it, do get into the chat. So keep your questions in Q&A. But if you've just got comments or other things you want to mention, I love to hear from you as I'm going through this, and I have the chat right in front of me as I'm talking to you. But let's not waste any more time. Let's talk about conquering complexity. And in order to conquer that complexity, we need to ask first, what is complexity? And I don't mean to be kind of too, I don't know, into myself as a developer or whatever, but I think our jobs are complex. Our jobs are mostly about, trying to model real life things inside a machine using a language that both we're supposed to understand as well as a computer's supposed to understand. The complexities of the things we're working on, and do shout out if you're working on anything particularly complex. I love to hear the kind of stuff you're working on. But the kind of things that we're working on have an enormous amount of complexity in their real world state. And then we add code on top of that. Code is inherently complex because it is this language that we've invented that both we're supposed to understand and the computer's supposed to understand. And the problem is that the computer gets to turn it into things it really, really does understand, zeros and ones and all that kind of stuff, whereas we still have to read stuff that other developers wrote or stuff that we wrote 12 months ago that we now have no idea what we were thinking at the time. And so that code is inherently complex. And it turns out, in order to actually maintain a decent velocity of writing code, a decent ability to change that code and to make progress building your application or fixing things that maybe have gone wrong, that we introduce a bunch of excess complexity. And so really our job becomes managing that complexity. Ideally, when we write something, when we write a piece of code to model something that is in our system or in real life, we only capture the amount of complexity that exists in that code itself. Adding excess or accidental complexity is what we're trying to avoid. And so our job is to manage that complexity. Rather sadly, it turns out that maybe in JavaScript, we're not doing that quite as well as we'd like to think. So I gave a talk last year in which I dug through the logs and things from SonarCloud and all the scans of JavaScript projects in SonarCloud to dig out the most common issues in JavaScript projects. Now, number one, not too much of an issue, really. It's probably just legacy code in which people are still using var instead of console.let. That's fine. It's probably not going to collapse our entire code base or make us worse at programming. However, the second most common issue that turned up in JavaScript code bases was that the cognitive complexity of functions is too high. And cognitive complexity, which I will get onto later, is that sort of measure of understandability. And when the cognitive complexity is high, it means that our functions are more difficult to understand. And that just slows down progress, makes it hard to actually change things, and makes it worse. And so I might say that the cognitive complexity of functions is too high, but that really begs the question, what is too high? And that brings with it an even more important question, really, which is how do we actually measure complexity? You might have some ideas about how to measure complexity in your own code bases. You might have used some tools to measure this before. If you have, again, shout it out in the chat box. I'm interested to see. But when we talk about measuring complexity, I can show you some code. This is a function that will sum up prime numbers underneath the function, the number that you enter as the argument to this function. How complex is this? How do you answer that kind of question? It doesn't look too bad. I mean, it's not too long a function. It's got some conditionals. It's got some loops in it. It's got some single letter variable names, which is not my favorite thing in the world. Maybe it's complex, but we can compare that. We can compare and say, we also have this function, a getWords function. We add a number in and it returns a piece of text for that number. So if the number's 1, it's going to return 1. If the number's 2, it's a couple. If the number's 3, a few. If the number's 4, many. If it's anything else, it's lots. Ideally, we'd put positive integers into this because it doesn't work for 0 and below. But that's not important. What we can see is that this is not a very complex function, I would say. This is nice and easy to understand. This one may be less so. But how do we really measure that? How do we, I don't know, put a number on that? That would be a nice way of doing it. You might have thought of cyclomatic complexity as a method to measure this. This has been around for a long time. Hopefully you have heard about it. It was invented back in 1976 in order to try and put a number on the complexity of functions and methods. And so cyclomatic complexity is defined as it adds a score for a function based on the number of breaks in that function, the number of loops or branches. In fact, actually, it scores 1 for being a function in the first place. And so if we look at our sum of primes function here, we score 1 for being a function. You always have the minimum cyclomatic complexity of a function is 1. But then as we hit for loops and conditionals, or any loops and conditionals, we also score additional points for that. So we score 1 for this for loop here. We score 1 for the second for loop. We score 1 for the conditional inside of that. And then we've got one final conditional, which is going to score 1. And it scores 5. Cyclomatic complexity of this function is 5. We can move on to our other function, which I think we probably, again, agree, getWords, probably a bit simpler. But in the world of cyclomatic complexity, we score 1 for being a function. Said that already. And then for each of the cases in the function, case of 1, 2, 3, and 4, we also score 1. Because those are also branches that the code can kind of traverse down. And so getWords and sum of primes are both scored as 5 in cyclomatic complexity. And that doesn't feel exactly right. It doesn't feel right because we can clearly see that this simple switch is less complex than our set of loops and conditionals in the sum of primes. So can we do better than that in order to kind of understand, well, the understandability of a function? This cyclomatic complexity really actually measures the number of paths through a function. Now that's useful. That's a useful number because it tells us some things. It tells us how many tests you'd need to write to fully cover that function. Like both of those functions would require 5 tests to get 100% test coverage on them. But as we've seen, it doesn't necessarily tell us about understandability. And that's what we'd really like to measure because understandability is how we interact with the code over time. If we can understand it, then we're more easily able to interact with change and improve our code over time. If we can't understand it, we spend a long time trying to understand it before we even get to the changing parts. And so that brings me to cognitive complexity, a score that I told you earlier is too high in many JavaScript functions. But let's find out how that score is made, at least at first. So cognitive complexity still gives a number at the end of the day for a function. It gives this idea of how complex it is, how hard it is to understand. And it creates that score by incrementing for breaks in flow, using loops and conditionals, much like cyclomatic complexity. But it also keeps in the back of its mind a nesting score, which it increments every time we nest. And when you increment for a break in flow, you add 1 for the conditional or the loop, and you also add what the current nesting score is. And so let's see how that works out with our two functions. So our sum of primes. First up, cognitive complexity doesn't bother scoring for being a function. If you think of cyclomatic complexity, it includes the number of paths that you can take through a function. A linear function will still score 1 because you can take one path through it. Meanwhile, we don't have to care about that when we're trying to understand it. And so we don't have to score for being a function, but we do score 1 for having a for loop. Now our nesting score has started as 0, but now we're going to add 1 to the nesting score in the background too. And so when we get to our second for loop, which is nested once, it's going to score 2, 1 for being a loop and 1 for being nested 1 deep. We're going to increment that nesting score again, and we get to our conditional, which now scores 3, 1 for being conditional and 2 for being nested twice. Now this would also increment the nesting as well, because we're going to go inside a third level of nesting for this conditional, but there are no further loops or conditionals in there. And so we'd actually then start decreasing the nesting. So that's now back down to 2, back down to 1 as we drop out of the for loop. Then we hit another conditional. So we go back up. So this is now nested once. So we score 1 for nesting, 1 for being a conditional. And then the rest of the function, no more loops, no more conditionals. We don't have to worry about it anymore. And so now our sum of primes function is scoring 8 total for cognitive complexity. Meanwhile, the getWords function, which again, I hope you agree with me that this is a lot simpler. This getWords function is going to score 1. It scores 1 for being a switch. It's one big conditional. It's one big conditional on one value, the number that we passed into this function. It turns out, if you were to rewrite this function as a series of if-elses, then we would score 1 for each of the ifs, because a conditional with an if could be on a different variable each time, a different value each time. Meanwhile, our switch is only the one value, and so we only have to think about one value at any one time. And so now our cognitive complexity for getWords is 1, our cognitive complexity for our sum of primes is 8, and that feels a bit more like it matches the complexity of those functions for the way we actually think about these things. And the way I've been thinking about this is that we end up with kind of like a brain stack. We end up with this stack in our head as we're trying to read through a function. And if we are reading through our sum of primes function, then we start having to add kind of things onto the stack. We hit our first loop, and we're like, okay, now we have to consider at all times that this could be running many times, and that our value of I, the variable I in this case, will be changing through that. We get to the second one, we have a loop through a number of and we have the variable j, which will also be changing. So I and j are both to be considered. Both of these loops are important. And we hit the conditional in there, and we're just adding things on top that we have to consider now. Is I less than j or something? I can't remember what the code does, but that's why I'd have to go back and read it in order to find out. And I have to be considering all of these things. Then things start to get easier as you kind of drop out of those loops, which is nice. But then you go back in, you're like, okay, I have to still be considering that first for loop. And now I'm considering whether it turned out that number was prime or not. And then finally, we can pop those things off the brain stack and carry on with our day. Now we understand what's going on. But the higher that stack goes, or the more times we go up and down in a stack, the more complex the function is. And the more our brain has to work to understand what's actually going on, whilst keeping all the context stored in our memory, in our short-term memory right there. And so optimizing what we do with our brain stack is very much where I'm going with this. And so that brings us to part 3, which is to conquer that complexity. What do we do? Well, first up, the important thing is to understand where that complexity is. And to do that, we're going to need some tools to do so. I don't expect you to work out cognitive complexity of functions in your head the entire time. No one is any good at that. We have tools for this. And so I'm just going to drop out of here. And over here, I've got some code. This is not a hugely interactive demo with the code, I'm afraid, but this is actually some code that I use in a different slide deck of mine that throws confetti onto slides. It's a JavaScript slide deck in Reveal.js, and yeah, it will throw confetti. And so we have this big function that runs on the end of a slide transition. And what it does is it checks a few things, collects some variables from the HTML, and decides how much confetti to throw. Lovely little function, although it turns out I've got a yellow underline there because I have SonarLint installed, and SonarLint is telling me right here that this function needs refactoring because its cognitive complexity is 16, and that's 15 is allowed. And so when I said earlier that the cognitive complexity of functions is too high, we have a threshold for that, and that threshold by default in JavaScript is 15. I think that's a pretty good threshold because you can write some quite complex code without hitting it. And in fact, I had to try quite hard to get to this point. Now, give it a lot of time. I think it's much easier to add complexity to functions. But in this particular example, I got to 16. And so in order to see like where that is, if you hit quick fix, you're going to go to show all locations for this issue. And that would bring up these numbers. I already had them loaded, apparently. But that brings up these numbers, which shows all of those breaks, all of those loops, those conditionals, those branches that we are adding complexity with. And then if you hover over them, you can see the score for them. So this big outside conditional here is scoring a +1. And then inside we have a ternary conditional, which is scoring +2, one for being nested once. We've got another ternary, we've got another conditional. We end up looping, we end up doing quite a bit of stuff here. This ternary is now too deep. And later on we have it nested. Oops, we have it nested quite deeply there with the +4, 3 nesting for this final like check if the time is right. It doesn't matter what this code does. What matters is that you can see if you have SonarLint installed, you can see when functions breach this threshold of 15 in complexity and consider whether that's the time to fix them. So let's go back to the slides because the next stage is actually to do nothing. If you understand where the complexity is in your code base, and SonarLint is great at showing that as you're writing it, but if you're using SonarQube or SonarCloud, then that can will scan your entire project and show you all the places where you have high complexity. Second stage is still to do nothing. Don't do anything about it yet. You see, that complexity is only actually an issue if you need to understand and change the code. Up until now, I would assume that your code is, for the most part, working. And if it's working, then that's fine. If you don't need to change it, then that's fine. It doesn't need to change. In fact, changing working code is a potential risk. You could turn it into non-working code, which would be much worse than just complex code. Complexity is only an issue if you need to change the code. And so when it comes down to the time where you need to fix a bug somewhere or add a feature to something, and you find you're working with a complex function, that's when it's time to clean as you code. It's time to clean up that complexity first before you then make the changes. Because if you find you are working with a complex piece of code, it's important to understand it, break it down into easier to handle pieces of code, and then make the change because it's much easier to make that change afterwards. And so this leads me to suggest that you refactor things first. Refactoring that code before you change it, again, will make making the change easier. But it also will mean that you understand that code much better, and it will be easier to understand the next time somebody comes along to change or fix something. Now, refactoring, in my opinion, is improving how the code works without changing what the code does. And this is important for a number of reasons. Refactoring, your code, you should never have to worry about what happens sort of within a function, as long as when you put the same things in, the same results come out the other side. the inside can be a black box for the most part. And that's why, if you want to rearrange that code on the inside of the function, the outside should never change, at least during refactoring. We're here to improve how the code works without changing what the code does. How do you know we didn't change the result of running the code? Well, that leads us straight into tests. I hope you're a fan of tests. I certainly am. I'm even a fan of test-driven development, writing tests first, so that can drive the design of your application. And I'm a big fan of the idea that test-driven development requires you to go from a failing test, red, to green, to a passing test, and then refactoring. That will be a great way to that's a great way of dealing with things. I did notice a hand go up there. If you have questions, pop them in the Q&A box. That's the best way to ask a question during the webinar. So yeah, I like test-driven development. You don't have to do it that way, but the important thing about this is that we have tests. If we have tests to cover what the function does and what the outputs are from a function, then we can change the internals of the function and know that it's still doing the same job. And it's important in that case that your tests are there also to test what a function does and not how it does it. If your tests have any kind of thing that reaches inside the code of a function and deals with like the internals, then when you change how the internals work, the tests will fail, and you won't have that same confidence that tests that only care about the outputs do. So make sure you test what a function does and not how it does it. You can see how that kind of mirrors or maps to the same as what refactoring does. Refactoring is changing how the code does it, but not what it does. And tests should test what a function does and not how it does it. They go hand in hand. And so, yeah, if you don't have any tests for a piece of code that you're working on and you need to refactor, that's absolutely step 0. You need to go and write some tests. There's many ways to go about that. Goodness, go get your AI assistant to go write some tests for you. That might help. I don't know. But the important thing is when you're writing tests for refactoring a piece of code is that the test must cover the existing behavior exactly as it is, even if it's wrong. We are absolutely in this refactoring stage trying to ensure that we do not change the behavior of the system. We just want to improve how the code works. If you change how the code works at the same time, then the test will break. And how will you know that you have indeed fixed anything if you're just breaking your old tests? So you refactor first. And then once you're refactored, once you have indeed committed all those changes to say, okay, this is now a piece of code that has passing tests that behaves exactly the same way as how I started, but has changed the internals, that's the point where we can then move on to make the change that you actually need to make in that code. You can go and fix things. You can change the tests, but only after you finish that refactoring step. But that's getting a little ahead of myself because I want to give you some tips on refactoring JavaScript code to improve your cognitive complexity. And so cognitive complexity very much punishes nested code. The deeper we nest things, the more stuff we stick on our brain stack, the more difficult it is to understand what's going on. And so our aim here is to reduce that nesting. Reducing the nesting of our code will allow us to think more clearly through it, break it into smaller bits, and understand those bits better. And so I have 4 tips here. The first one is to invert conditions and exit early, structural collapse, extracting helper methods, and then using a couple of other language features that I think are really cool for this in JavaScript particularly. So let's jump into those. Inverting the condition and early exit. I showed you that code earlier that has this on-slide transition end, and we had this big that's not working. Had this big big conditional around the outside of the code. The whole function starts with this big if there's confetti in the current slides data set. And that's great, but it sort of immediately nests everything inside that first conditional. And you're always considering, is there confetti in the data set? What you can do instead is, of course, invert that condition. Say if there's not confetti, then we simply return. We get out of here. We're done. And that's brilliant. We've kind of dropped off having to consider whether there's confetti in the current data set. If there's not, we've already left. And so we can just get on with the rest of the function, which is to throw some confetti on the screen. We're ready to do that. We're going to do that. We've reduced the nesting and things are a lot happier. So we just pop one little thing off the brain stack there. We've got rid of one conditional. We are happy to just exit early instead of keeping that around in our mind, keeping that at the bottom of the stack. Next up is structural collapse. This is kind of where this doesn't have to be around the outside of a function again, like this code shows. But what's happening here is we've got two conditionals, one after each other, with nothing else happening in between. And that means that we can turn that two conditions into just one condition. And we only have to deal with kind of one idea of what's happening at this time, rather than the idea that there could be other stuff going on between these conditions. All we need to know is at this point, and this is sort of some made-up code here, is there confetti in the slide, and the media query says that animations are fine. In that case, we can animate some confetti on the screen. If we combine those conditions, we drop one level of nesting, and we only have one thing to think about on that brain stack, or one thing to add to the stack there. Rather than two, we can pop that second conditional off the brain stack, and we're in a happier place again. Next is probably, I think, the most important one in terms of refactoring for complexity like this, and that's to extract a helper method. It helps with duplication, but it doesn't necessarily need duplication to exist. It helps you to break down a function into its component parts, and allows you to kind of decrease the amount of context that you have to consider when you're dealing with each of the individual functions. And when you are changing or fixing something inside of a large complex function, if you break it down into smaller functions full of helper methods, then you probably find that what's broken or what needs adding is part of one of those smaller methods, and so it's easier to deal with. In this case, the code on screen is two ternary functions that I have. Two ternary expressions that I have, which are both doing the same thing. We've got the slide. We're looking inside the data set for a particular attribute. And when we get that attribute, we parse it as an integer. If we don't get the attribute, we return a default integer. And so we can turn that into a well-named function. That's one thing we can do to make things a lot easier to understand. In the code now, I know if I'm getting an integer data attribute or default, I can use this function, and I don't have to understand how it's going about it. I didn't have to drop the ternary. That's still part of the original function, but I've reduced duplication in my code by extracting as a helper method, but I've also dropped out a couple of conditionals from my code, and now I just understand that this is going to return me either an integer that was in the data attribute or a default number that I added at the end. The important thing, as I said, in these helper methods is that we're reducing the context. If you extract a helper method from a function and it brings the entire context of the existing function with it, then it's still just as complex as we started with, and now we're just moving code around. In fact, it's probably harder to deal with that because you're now trying to handle a helper method that has gone somewhere else, but still requires all of the context. And so extracting a helper method should reduce that context, and ultimately pop some of that context off of our own brain stacks and make it a lot happier. Finally, there's some language features. There's some language features we can use which are going to make things slightly easier as well. The first one is if you have nested objects and you need to get a property that's deeply nested inside of an object, you used to have to do this kind of thing where you'd have to check that the first object exists within, that the second object exists within the first, and then the property exists on that object. And we've got this Boolean and it can go deeper and deeper, and ultimately looks quite ugly, but also is adding complexity to things we're having to understand. But now in JavaScript, we have optional chaining, which allows us to optionally chain all the way through a deep set of properties and objects in order to get something that's at the bottom. We dig out a property at the bottom of a set of nested objects. If any of the question mark dots fail at any one point during that, it just returns undefined, as you'd expect, without you having to do a whole bunch of tests to find out if everything was there. And so optional chaining, very nice to just simplify things. And then secondly, there's this idea. If I have an object here, I've got some defaults that I had set up. And then if this bit then checks if the defaults colors is still undefined or null, that is, it hasn't been defined, or I've defined it as something that is null, then we can reach into the DOM, into the page to get, in this case, an array data attribute or default, and get some colors out of there. This is great, but like it's adding a conditional to our thing, and we don't have to anymore, not with the nullish coalescing assignment operator. That's our little double question mark equals there, which says, hey, if default.colors is not already assigned to something, then we can assign it to this. And that checks for null or undefined. Simplifying things, dropping that conditional, and popping things off the brain stack. I am running a little out of time here, but I have a quick bonus rant for you as well, because nested ternaries have got up in my mind recently, and I don't like them. Nested ternaries look like this, where we have, there's 3 ternaries there, and I don't like it. It sounds so at the end of last year, Prettier, the formatter, actually came up with a new way to format nested ternaries because people were unable to consider that, unable to agree on a good way of doing so over many years. And this is the way they came up with, and I still don't like it. And the main problem is nesting is bad. I still don't like nesting. It's extra complex. But in this case, like reading this through, at least to me, says, okay, we've got this pet, and if it can bark, then we have and if the pet is scary, then it's a wolf. Otherwise, else it's a dog. Else, and we've got to drop out of that. If it can meow, it's a cat, and otherwise it's probably a bunny. Okay, I'm happy I got through that, but I didn't like it. There are many better ways, I think, to deal with nested ternaries, and one of them, and a few of them, kind of deal with the a couple of the refactorings that we've just gone through. So if you actually were to extract this ternary as a function itself, as a helper function, then it's something that you can actually test independently, which I think is a really useful factor of that. But then we can also use that idea of using conditionals and exiting early. And so this now reads, I think, a lot easier in that case, in the case where if a pet can bark and is scary, then it's a wolf. Otherwise, if a pet can bark, then it's a dog. Otherwise, if it can meow, it's a cat. Otherwise, probably a bunny. And I'm fine with that. That's much easier to read, but it's also easier to test. And it's also easier then to use that function elsewhere in your project. And so I don't like nested ternaries. I think they should go away. I have no problem with ternaries as such, but nested ones can get out of my code base. Thank you very much. Okay, so what have we covered here? We had a little talk about what is complexity, mainly our jobs and code. We asked, how do we measure complexity? And I posit to you that in terms of how we understand code and how we work with it, cognitive complexity is a useful measure. Cyclomatic complexity is also a useful measure, but more about code coverage and the ability to understand the number of branches you have in a system. And then finally, we looked at conquering complexity. We refactor, we ensure we have tests, we refactor code first using refactorings like extracting helper methods, structurally collapsing conditionals into each other, early exiting, and using other kind of optional chaining or nullish coalescing functions in the language. And once we have conquered that complexity, when you are making changes to code, we refactor first, we make it easier to understand the code, and then we make the change, and making that change becomes easier, not just there, but for the future, for future code as well, for future developers on your project, for yourself in the future. There are tools, of course, to help you out with this. As I showed, SonarLint can show you when you're writing more complex code as you're coding it, as well as applying hundreds of other rules to your code at the same time to help you out, help you writing clean code. And then SonarQube and SonarCloud will live there, can live there in your CI and CD pipelines to catch complexity, as well as all those other things that that can go wrong in code as you push to your DevOps pipeline. I got some other links for you, which have just been popped into the chat right there. That was magic. There's a paper that was written back in 2016 on cognitive complexity, and I actually highly recommend reading it if you are interested in this at all further. It's a very good read. I don't normally read computer science papers, honestly, but I've read this one several times, and it's a great read. And it will give you a few more details and a few more kind of bits we look at in terms of cognitive complexity at Sonar. And then because I included the bonus rant, I've also got the blog post I wrote up on stop nesting ternaries. Highly recommend going and reading that. And if you disagree with me, not leaving a comment. So that's all I've got for you this evening for me. Again, my name's Phil Nash. I am a developer advocate here at Sonar, and I'd love to hear your questions. But right now, I'm going to pass back over to Andrew to finish things up.
Phil, thanks. That was awesome. You certainly did help us understand how we can conquer complexity, and I particularly love how we can recognize complexity as we're coding and then resolve it almost before it becomes an issue later on. So thank you for that. As we move into a time of Q&A, and I just checked to see if we've answered all the questions during the session or not, I did just want to briefly put on the screen some of the upcoming webinars that we have, particularly the first one. It's a hot topic, writing cleaner using AI coding assistance with Sonar. So that's something that people may be interested in. Anyway, let's just check on the questions. We haven't got an awful lot of time, but I would like to just check on those. Perhaps to kick us off, Phil, what do you do if a framework encourages nesting and complexity? So you're almost having to start with that.
Yeah, that is an interesting question. Like, I'm certainly aware that yeah, some patterns are encouraged by frameworks that maybe would be picked up or quite obviously kind of nested in terms of this cognitive complexity thing. Now it turns out that we are aware of this, and we actually our fabulous JavaScript team who works on the analyzers and works on making sure this is the case are very much JavaScript and TypeScript developers themselves, and have spent time in these applications. And so we work with both our own internal knowledge, but also feedback to ensure that cognitive complexity doesn't complain too much when it doesn't make sense, when it is indeed some part of the framework or the way that it is conventionally written. Convention is actually an important part of how we see clean code. Clean code we kind of define as code that is consistent and adaptable and intentional and responsible. And under consistency is convention. The best way to write code that's going to be understood is to write it in the conventions of the language or framework that you're working in. And so if a framework is encouraging that kind of thing, then we will put in exceptions in terms of cognitive complexity to ensure that it's not that Sonar is not complaining about things that shouldn't be complained about. I think it's really useful because, like, this cognitive complexity, so cyclomatic complexity is this very kind of rigidly defined number of paths through a system kind of score, whereas our cognitive complexity is actually more of this heuristic about how understandable a piece of code is. And if you are working within the confines, within the conventions and within the conventions of a framework or a system, then we don't want to complain about that. It's a heuristic for understanding. And if you are writing conventional code within that framework, then it will be more understandable. So cognitive complexity is malleable in a way, and will work to help you.
Great, thank you. Just checking the other questions. I did love your rant, by the way, at the end. Nested ternaries. I don't know what your problem is. I'm sure you're up for a debate with anybody who wishes
Always.
to have one. Come and grab you at the next conference, right?
Yes. In person is much more fun because we can do it over a cup of coffee or a beer or something. I don't know.
That sounds great. Well, Phil, thank you so much. I appreciate your time. I know you're always traveling, so it's great to be able to catch you and use you for this webinar. And thanks to all those who've attended and posed questions. If you do have any other questions, our community is a great place to pose them, and also to review other questions that have been posed in the past and answered, you can contribute to that ongoing discussion. And also do visit sonarsource.com for further information on some of the topics that Phil mentioned. He mentioned Clean as you code, for example, as well as SonarLint and the other Sonar solutions. So you can also check out that, and also our other webinars, and also places where Phil will be appearing in the near future, I'm sure. And thank you again, Phil, and thanks for attending, everybody, and for providing your feedback, which we do consider a gift, via the survey that will shortly pop up on your screen. But let me just end by saying big thank you for Phil and for delivering that excellent webinar on conquering complexity. Thanks, Phil.
Thanks very much, everyone.